Hi everyone. In this lesson we're going to discuss hypothesis testing for a population mean mu, and we're going to develop a technique to perform hypothesis testing. Now first we need some background information. So note that in statistics a hypothesis is a claim about a property of a random variable or population. For example, suppose we're given a random variable x in which the value of the mean, mu, is unknown to us. Now perhaps it's claimed that the mean is equal to mu naught for some conjectured number mu naught. So that would be given to us. For example, mu equals 10. Now we call the claim that mu equals that number mu naught our null hypothesis, and is denoted by H0. So that is our null hypothesis. Now we may want to test that claim against an alternate claim like the population mean does not equal mu naught, or the population mean is actually less than mu naught, or the population mean is greater than mu naught. Now all of these are called alternate hypotheses, and they're denoted by H1. Now keep in mind that when we do hypothesis testing, we set up our null hypothesis, which is a statement involving equality like this right here. And for our alternate hypothesis, we pick one of these. We don't use all of them, we just pick one of them depending on the type of test we want to perform. Now what we need to do is to determine which claim, H0 or H1, we should reject and which one we should support. For example, suppose a farmer knows the average yield for corn planted with fertilizer type A is 180 bushels per acre. And recently the farmer has switched to type B fertilizer, and they would like to know if changing fertilizers has changed the average yield per acre. So they might set up a hypothesis test like this. H0 would be that mu equals 180, so the average yield per acre has not changed from 180, it is still equal to 180. And they might test that against the alternate hypothesis that the average yield per acre is not equal to 180, so it has changed. Or they could test it against the alternate hypothesis that mu is less than 180. That's if they think the yield has decreased. Or they could test against the alternate hypothesis that mu is greater than 180. And that's if they think the yield has increased. So you have three types of alternate hypotheses that you could test against the null hypothesis that the yield is still equal to 180. So that's an example of how you might set up a hypothesis test. Now we need to develop a technique that will tell us, should we reject H0 or should we reject H1? Now in this lesson, we're going to discuss hypothesis testing of this type. That's hypothesis testing of means when the population standard deviation sigma is known. In subsequent videos, we're also going to discuss these three types: hypothesis testing of means when the population standard deviation sigma is unknown, hypothesis testing of population proportions, and hypothesis testing of population variances. So that's the four types of hypothesis testing that we're going to cover in this module. And in this video, we're going to be discussing this type of hypothesis testing, and we're going to develop a technique for this type. Now to develop our technique, let's first note this. Suppose we have a random variable x for which we do not know the population mean, as we discussed previously. And in addition, suppose it is hypothesized that the mean is some given number, mu naught. Now, as a researcher, you would like to test the null hypothesis, mu equals mu naught, against an alternate hypothesis like mu does not equal mu naught. Now, we're just going to focus on this type of alternate hypothesis for the rest of our discussion, and then we'll discuss how we can modify our technique to cover the other two cases where mu is greater than mu naught or mu is less than mu naught. So we'll cover those later. For right now, we're just dealing with this type. So the question is, how do we do this? Well, it would be natural that you would take a survey and calculate a sample mean, x bar. Now for our discussion, suppose that mu naught is 10. And you go out and you take a sample mean, and you find out that your sample mean is 9.5. Now the question is, based on this 9.5, do we reject the claim that mu is actually equal to 10 or not? You see, it's natural that our sample mean is not going to exactly equal 10. It would be highly unlikely that our sample mean would be exactly equal to 10 if we have a large population. So naturally it's going to differ somewhat from this number. So the question is this number 9.5 significantly different from 10? If it is significantly different from 10, then it would be natural that we would say the claim that the mean is equal to 10 is probably wrong. And then we would reject H0. So, as we have written down here, if 9.5 is significantly different from 10, then we would reject the claim that the mean is equal to 10 and state that the data supports the alternate hypothesis that mu does not equal mu naught. Otherwise, if we determine that 9.5 is not significantly different from 10, then we would fail to reject H0, and we would state that the data supports the null hypothesis. So we see that in order to perform hypothesis testing, what we really need to do is to find a method to determine if our sample mean is significantly different from the hypothesized mean of mu naught for some given number, mu naught. Now we can develop a technique to do this. Now here's where we actually begin the development of our hypothesis testing technique. So suppose we're given a random variable x for which the mean, mu, is unknown, but the population standard deviation, we're going to assume that is known. And there could be a good reason why we can assume the population standard deviation is known in certain situations, and later on we'll develop a technique for hypothesis testing where we do not assume that sigma is known. But for right now, just assume it is known. Now, we want to test this null hypothesis that the mean, mu, is equal to some conjectured number, mu naught. Now what we're going to do temporarily here is assume that this really is true, just for the time being. So we take a sample of size n, and we evaluate a sample mean x bar. Now, by the central limit theorem, for n sufficiently large, as a general rule, n should be taken bigger than 30, or if n is not bigger than 30, as long as we assume x is close to being normally distributed, then these numbers, the z-scores for x bar. So if we evaluate the numbers x bar minus mu naught divided by sigma over root n, now that's assuming the population mean really is mu naught, then these numbers should be very close to being normally distributed with a mean 0 and a standard deviation 1. That's by the central limit theorem. Now, recall that for the standard normal distribution, 95% of all of your scores will lie between negative 1.96 and positive 1.96. So in other words, the probability that this number up here, when you calculate it, is between negative 1.96 and positive 1.96 is 0.95. So the probability of this occurring right here is 0.95. Now that's assuming for the moment that the population mean really is mu naught. And correspondingly, assuming the population mean really is mu naught, the probability that your z-score is less than negative 1.96 or larger than positive 1.96 is 0.5. Now based on this, we can develop the following hypothesis testing technique. So we're basically going to do this. You calculate your sample mean x bar, and then you evaluate this number z. That's your test statistic, or your z-score for x bar. If that number falls between negative 1.96 and positive 1.96, then nothing unusual has happened, because we would expect that to occur given that the population mean really is mu naught with a probability of 0.95. So nothing unusual has occurred to make us think that the population mean is not mu naught. On the other hand, if you're in this situation or this situation where the z-score is less than negative 1.96 or larger than positive 1.96, then something unusual has happened, because this is a low probability occurrence, assuming that the population mean really is mu naught. And if this occurs, that makes us think then that, well, maybe the population mean really isn't mu naught, because this is a rather rare occurrence. So if this occurs right here, we are going to fail to reject H naught. And if this occurs down here, we're going to reject H naught. And that's basically how our hypothesis testing works. It's pretty easy. We just have to calculate this number right here and compare it to negative 1.96 and positive 1.96. Now here's the full procedure in the next slide. Now here's our method for hypothesis testing. A null hypothesis, like mu equals mu naught, against an alternate hypothesis, mu does not equal mu naught, when your population standard deviation sigma is known. So the first thing you do is you take a sample and you evaluate x bar. Then you calculate this quantity right here, that is the z-score for x bar. Notice we have the mu naught right here, and the population standard deviation is right here, and that is your sample mean and your sample size, n. Now, if this test statistic, that's what we call it, falls between negative 1.96 and positive 1.96, then nothing unusual has happened to make us believe that the true population mean is not equal to mu naught, because this is what we would expect 95% of the time if the population mean really is mu naught. And so we fail to reject H naught in this case right here. And then we say that the alternate hypothesis H1 is not supported by the data. Now, if your test statistic is smaller than negative 1.96 or larger than positive 1.96, then something unusual has happened, because if the population mean really is mu naught, then this would only have a 5% chance of occurring. And so that leads us to believe that the true population mean is not equal to mu naught, and so we reject the null hypothesis in this case right here. And we conclude that the alternate hypothesis is supported by the data instead. And that's it. That's all that there is to hypothesis testing in this case where sigma is known. And just note one other thing. Sometimes this region right here, that's called our critical region. It is also denoted sometimes by the absolute value of z is greater than 1.96. You see this is equivalent to this occurring over here. And this can also be written as this region right here, negative infinity to negative z alpha over 2 union z alpha over 2 to infinity, and that is called our critical region, or the rejection region for H naught. Now, before we go over some examples, let's clarify some definitions that we've covered so far in our discussion. Now, in our discussion, the value alpha, which we used 0.05, but that can change, is called your significance level. And common values that are used are 0.1 or 10%, 0.05 or 5%, and 0.01 or 1%. Now take note of this also. This is an important point. The significance level is the probability of incorrectly rejecting the null hypothesis if it is true. That's what your significance level represents. And to see that, let's consider this graphic that we have on the next slide. You see right here we have our standard normal distribution. Now if the null hypothesis really is correct, then the z values which you calculate right here should have a mean of 0, which is right here. Now there is a chance, even if the null hypothesis is true, which means that the mean for these values is 0, there is a chance that your test statistic could land out here or out here in your rejection region. And the probability of that happening is alpha. You see the area out here is alpha over 2. The area out here is alpha over 2. So the probability that your test statistic lands out here, given that your null hypothesis really is true, is alpha. There is a chance of rejecting the null hypothesis when it really is true, and that probability is alpha, and that's your significance level. So that's what the significance level represents. It's the probability of incorrectly rejecting the null hypothesis when it actually is true. Now also in our discussion, the value 1 minus alpha, which in our previous discussion we used 0.95, that's called your confidence level. And that can be adjusted. Common values are 0.9 or 90%, 0.95 or 95%, 0.99 or 99%. Those are common values that are used. Now also note that the confidence level is the probability of failing to reject H naught if it is true. And also notice from our graphic that we had looked at a few seconds ago, once again considering this graphic right here, if your null hypothesis really is true, if the mean really is mu naught, then the mean of your z-scores is 0. And so you see the probability of your z-score landing in the region where we fail to reject the null hypothesis is 1 minus alpha, which in our previous discussion was 0.95 that we used, but it can be changed to other values. And so you see the probability of failing to reject the null hypothesis when it really is true which is what you want to do, is 1 minus alpha. So that's what your confidence level represents. It's the probability of failing to reject the null hypothesis when it really is true. Now, in our previous discussion, the values negative 1.96 and positive 1.96 are called your critical values. Those were the cutoff values between the rejection region and failure to reject region. Now, those values are determined by your significance level alpha, and on the next slide we'll see that we calculate these just like we did previously for confidence intervals, where if we're using Excel we use the norm.inverse function, so they're calculated just like we saw when we were studying confidence intervals. And for the type of test that we discussed, which was a two-tailed test, they are denoted by Z alpha divided by 2. And just note that for the standard normal curve, the area in each tail, that is the area to the left of negative 1.96 and to the right of positive 1.96, both of those areas are 0.025, so they add up to 0.05, which is your significance level. For example, if we look at our next slide quickly, you see here we have our standard normal distribution, and if this critical value right here is 1.96, then the area to the right of 1.96 is 0.025, and if this value over here is negative 1.96, then the area to the left of negative 1.96 is also 0.025. And you see if you add these two areas up, you get our significance level, which in the development of the hypothesis test, we used 0.05. And so that's how the 0.05 is related to the area in the two tails. And in this case, we have a two-tailed hypothesis test. And down here we have our critical values for other significance levels. For example, with a significance level of 0.1 or 10%, your critical value, the Z alpha over 2, is 1.645. 0.05 we see is 1.96, and 0.01, which corresponds to 1%, is 2.576. We also have listed over here one-tailed critical values, and we'll talk about these soon. For a one-tailed test, you don't have one of these tails up here. For example, for a right-tailed hypothesis test, a hypothesis test which would look something like this, so right here we have a right-tailed hypothesis test, which we will mention shortly. In this case, you would not have this critical region over here. It wouldn't be here. You would only have one critical value, and if your significance level is 0.05, then you would want the area in this tail to be completely 0.05, in which case your Z alpha value would be 1.645. And also notice that we call it Z alpha now instead of Z alpha over 2 because we only have one critical region and the area in that critical region is entirely alpha instead of having it split up between two critical regions. And once again, the value Z, which is x bar minus h0, your null hypothesis, divided by sigma over root n, that is called your test statistic. And this is used to determine whether you reject or fail to reject the null hypothesis. depending on whether it lies in the critical region or not. Also, the region z less than negative 1.96 and z greater than 1.96, written either like this or like this, that is called your critical region. And if your test statistic up here falls in this region, then you reject the null hypothesis. Now, in our development of hypothesis testing, we had two critical regions. You see this one here and this one right here. And because of that, we call this a two-tailed test, but you can also have one-tailed test, which is what we'll discuss soon. So those are a few definitions that we have covered in our discussion so far. Now, when you're doing hypothesis testing for a sample mean, there are three different tests you can set up. In our development of hypothesis testing, we focused on the first type that we have listed here. This is called a two-tailed test. You notice our null hypothesis is mu equals mu naught, and we were testing it against the alternate that mu does not equal mu naught. So that means that if we calculate a sample mean, and then from that we calculate a test statistic z, if our sample mean falls significantly to the left or right of mu naught, then we reject the null hypothesis. Correspondingly, if our test statistic falls in the left critical region or the right critical region, we reject the null hypothesis. Now, this is sometimes called a non-directional hypothesis test because we can reject the null hypothesis if our sample mean falls significantly to the left or to the right of mu naught. So we don't really care about the direction it falls in order to reject the null hypothesis. Now, we can also set up a left-tailed hypothesis test like we have here. So notice in this case we only reject the null hypothesis if our sample mean falls significantly to the left of mu naught or is significantly smaller than it. Now, that's the same as saying your test statistic z falls in a left critical region, and we have an illustration of that on the next slide. We can also set up a right-tailed hypothesis test where we only reject the null hypothesis if our sample mean falls significantly to the right of mu naught, or correspondingly our test statistic falls in a right critical region. So those are the three types of hypothesis tests that we can set up. Now, here we have a slide illustrating the difference between a two-tailed test, a left-tailed test, and a right-tailed test at a significance level of 0.05, and also keep in mind that we're assuming sigma is known for our discussion here, which will change later. Now, when you do these tests, for each one of them you calculate your test statistic right here, and for a two-tailed test you set up your hypothesis test like this, and if your test statistic falls in one of the two tails right here, then you reject the null hypothesis and you state that the data supports the claim that the mean is actually different from mu naught. Otherwise, if your test statistic falls in this region, in here, then you fail to reject the null hypothesis. For a left-tailed test, you set up a hypothesis test like this, and if your test statistic falls in this left tail right here, then you reject the null hypothesis, and you state that the data supports the claim that the mean is actually less than mu naught. Otherwise, if your test statistic falls in this region, like right in here, then you fail to reject the null hypothesis. Even if your test statistic falls way out here to the right, you still fail to reject the null hypothesis. Only if your test statistic falls in the left tail do you reject the null hypothesis in this case. Now we also have a right-tailed test down here. This is how we would set that up. So for a right-tailed test, we would only reject the null hypothesis if our test statistic falls in a right tail, like we have illustrated right here. So if our test statistic falls in this region, we would reject the null hypothesis and state that the data supports the claim that the mean is actually greater than mu naught. Otherwise, if our test statistic falls in this region over here to the left of our critical value, then we would fail to reject the null hypothesis. Also take note how our critical values change in each of these tests. For a two-tailed test, our z alpha over 2 value is 1.96, and that's because we want the area in the right tail here to be 0.025, and that's for a significance level of 0.05. Notice we have two tails. Each tail has to have an area of 0.025, which is half of 0.05. And so our critical values are plus and minus 1.96. For a right-tail test, we only have one critical value, and the z alpha value is 1.645, and that's because we want the area in the right tail here to be 0.05 as opposed to 0.025 for a two-tail test. And for a left-tail test, our critical value is negative 1.645, and that's because we want the area in this left tail to be 0.05 as opposed to 0.025 for a two-tailed test. So take note how our critical values change. And also keep in mind that the z alpha over 2 and z alpha value will change for different significance levels, of course, and you can calculate them using the norm.inverse function in Excel. And here we have a nice summary table of hypothesis testing for the case when the population standard deviation sigma is known. So each row represents the type of test that you're going to perform: a two-tailed test, a right-tailed test, or a left-tailed test. So for a two-tailed test, you have your null and alternate hypotheses set up like this. You calculate your test statistic, which is the same for each case. And then you compare the test statistic to your critical region. Now for a two-tailed test, you have to calculate the z alpha over 2 value, and the alpha, remember, is your significance level. Now down here we have common critical values for the two-tailed test. For example, for a significance level of 0.1, it's 1.645, 0.05, it's 1.96, 0.01 is 2.576. So in the two-tailed test, you take the absolute value of your test statistic and compare it to z alpha over 2. If this condition is satisfied, that means that z falls in the critical region and you would reject h0. Similarly, for a right-tailed test, you would set up your hypothesis test like this. You use the same test statistic right here, and you compare your test statistic to the critical value, z alpha, and if this condition holds, you reject h0. For a left-tailed test, you set it up like this, calculate your test statistic, and if your test statistic is less than negative z alpha, then you reject h0. So this is a nice summary table for you to use with hypothesis testing. Now over here in this column we have what's called the p-value. We haven't talked about that yet, but we will after we do an example. This is a very quick way to determine if you should reject or fail to reject the null hypothesis. So each of these Excel commands will evaluate what's called the p-value for your hypothesis test. And all you have to do is compare the p-value to your significance level alpha. If the p-value is less than alpha, you reject H0. It's as simple as that. So you notice with each of these commands, you do have to calculate your test statistics still. That's the Z right here. But then you just evaluate this command or this command or this command using Excel. And if the number you get back is less than alpha, you reject H0. It's as simple as that. And we'll talk about this right after we do an example. And keep in mind down here we have a table for the Z alpha over 2 and Z alpha values for various significance levels. Now these are the most common ones that you'll run across for 0.1, 0.05, and 0.01, or 90% confidence level, 95%, and 99% confidence level. If you have to calculate other Z alpha over 2 values for values like 94 or 97%, say, then you can use these commands right here to do that for either a two-tailed test or a one-tailed test. Now before we look at our first example, let's take a look at a few important points here that we should remember about hypothesis testing. First of all, H0, that's called our null hypothesis. H1 is our alternate hypothesis. We also enter a hypothesis test assuming that H0 is true. So H0 is assumed to be true until we perform a hypothesis test and conclude that it should be rejected. So we always enter a hypothesis test assuming the null hypothesis is true. Also keep in mind that the smaller your significance level alpha is taken, the more difficult it is to reject the null hypothesis. So in other words, the stronger the evidence from the data needs to be in order to reject H0. And you can see that if you look back at this graphic. You see right here we have our graphic for the two-tailed hypothesis test. And as you take the significance level smaller, what's going to happen is these critical values right here will move to the right and to the left. And so it will become more unlikely that your test statistic falls in the rejection region then. So as your significance level is taken smaller, your critical values move to the right and to the left, and it will become more unlikely that you reject the null hypothesis. Also keep in mind that you either reject or fail to reject the null hypothesis. You don't state that H0 or H1 are true or false because we do not normally know that with 100% certainty. So if you conclude that you should fail to reject H0, you can state that the data supports H0, but you don't want to state that H0 is true. You just want to state something like the data supports the null hypothesis. Similarly, if you conclude that you should reject the null hypothesis, you can state that the data supports H1, but you don't want to state that H1 is true. Also note that H0 should be a statement involving equality like this. This is normally what we use for the null hypothesis. However, sometimes you might see people write the null hypothesis like this or this. This one here, where mu is less than or equal to mu naught, corresponds to a right-tailed test. So you would see your alternate hypothesis written as mu is greater than mu naught. And if you see someone write this for the null, then your alternate would be mu is less than mu naught. You might see that sometimes written as well. Now also note that H1 should be a statement either involving not equal to, less than, or greater than. That's what your alternate involves. And that concludes our discussion about the background information needed to perform hypothesis testing. Now, in the next video, we're going to take a look at a few examples.